Hello everyone. In this video we are going to talk about DMU or digital mockup kinematics analysis in CATIA. So if you ever made a mechanism or a system of mechanical components that are assembled and they are moved to achieve some goal, like a mechanism, a robotic arm, or anything like that, you might want to basically do some kinematics analysis on it, right? You want to know, for example, if you have some specific input, then what are the outputs, what are the position, acceleration, velocity, whether linear or rotational of the other rigid bodies and so on. Generate some plots, correct, and generate some laws for the inputs, like inputs as a function of time. Do some plotting, as I said, look at the degrees of freedom and so on. And that can be accomplished in CATIA DMU Kinematics Workbench. So here is a 4-bar linkage that I have assembled ahead of time. And I have not added pins because they do not play really any role in kinematics of this 4-bar linkage. And as you can see here, I have 4 links. The green one is the ground, which is fixed. The yellow one is the input, the blue is the output, and the red one is the connecting rod. And if you rotate the input, then the con rod and the output will rotate as well here. And then depending on the length of these different members, you can have different types of the motions for this 4-bar linkage. So the input link can do full rotation, which we call it a crank. The output can also do full rotation, or in this, which we call it then crank mechanism. If the output only oscillates between 2 positions, then we call it rocker. So it's going to be crank rocker, like in this case. You see the yellow member goes full rotation, but if you see, blue member only oscillates between 2 angles. So this is a case of crank rocker mechanism, based on the video I made for determining the degree of freedom for a mechanism based on the Grubler formula. Just watch that video I published, and it is inside the playlist for dynamics on the channel. You know that this whole mechanism has 1 degree of freedom, so once you know the angle of the input, you should know the angle of the con rod and the output. Okay, so this is our mechanism. It's properly assembled, and now we're going to take it to DMU Kinematics and try to do analysis on it. Make sure your assembly is correct. If your assembly is not correct when you take it to DMU Kinematics, you have to fix it there, and otherwise you're going to get some error. So here we go to Start, we go to Digital Mockup, and then we go to DMU Kinematics. And this is the environment where you can do analysis on the mechanism here. And I'm going to show you that. So I'm trying to get for you the important toolbars, which are mostly on the right side. So the first thing is you had these constraints. But in DMU Kinematics, what you have are joints, basically. You have to create different types of joints. And the joints will be created from these constraints, right? So, for example, you know here that this hole and the hole on the ground link, they are coincident. And these 2 planes are coincident as well. So what you really have here is a revolute joint, correct? And you have revolute in other places too. So that's one type of joint, but there are other types of joints as well. So if you have a revolute joint, it has 1 degree of freedom. If you have a prismatic joint, which is only sliding along one direction, that's also 1 degree of freedom. If we have a cylindrical joint, it has 2 degrees of freedom. Not only one object can rotate within the other one, it can also move backward and forward, just like the cylinder in the piston inside the cylinder. It goes up and down. It can also rotate a little bit. If you have a spherical joint, it has all 3 rotations, but no translation. If you have planar joint, then you have one rotation perpendicular on about an axis perpendicular to the plane, and two translations along the axis on the plane. If you have a free body diagram, you know it has 6 degrees of freedom. If you have a fixed or rigid joint, it's like welding or pivoting it down or bolting it down, then it has 0 degrees of freedom. So the first thing is you have to create these joints out of the constraint that your assembly has, and you either do it automatically or you will do it manually. Okay, so first let's see if we can create these joints automatically, because they can be created from this constraint of the assembly. So what you need to do is on this toolbar here, go to this command right below the fixed part. It says assembly constraints conversion, and you click on that, and when that guy comes up, you have to select your mechanism. If it's not there, then you say new mechanism, and then choose this mechanism number 1, which is this guy, and it shows how many unsolved pairs you have right now. And when you say auto create, if there is any problem here, if it could not make any joints, then this is not going to be 0 out of 4, it's going to be 1 or 2 or something. So if you see any number other than 0, it means it could not convert all of your constraint into proper joints. Right now there is nothing unsolved, so it means the conversion was successful. Okay, and it has more controls over it, but you clearly can as you can see here, you can clearly create the joints that you want, and we can go and check them. So I guess I should have said okay, not cancel. So I've created them, and now if you go here down to Applications tab, go to Mechanisms, Mechanism 1, then it shows under Joints the joints that has been created for you, and as you can see, one of them is kept cylindrical, the 3 of them are revolute. If it made all of them revolute, then you're gonna have problems for the degree of freedom. Okay, because this problem is not actually 2D, this is a 3D problem, and if you again have all of them revolute, then you cannot properly rotate the mechanism. So it decided that one of them should be left as cylindrical, although it's not really moving anything forward or backward, but that keeps the degree of freedom such that it can move. And whatever one of these you want, you can double click on it and it shows where it has been created. So this one is between the conrod and the input. You can clearly see that, right? The cylindrical here is created between the ground link and the output, and so on and so forth. So you can see where they are created. It shows the degree of freedom for your entire mechanism. As you can see, it is 1. Okay, so you have 1 input to provide in order to determine everything in this mechanism, any position, velocity, acceleration, and so on. So you have 1 degree of freedom, and that's exactly what we know from dynamics. Okay, so as you can see, I could easily and properly create these joints automatically from assembly. But as I said, you can also create them manually, and to do that, right above this fixed part, there is this revolute joint, but if you expand it, there are all sorts of joints that you can create manually if you want. So there is revolute, there is prismatic, cylindrical, screw joint, and the screw is different from cylindrical. You know, screw joint has 1 degree of freedom. Although the screw goes inside the other part, the nut, backward, forward, and it spins also, that spinning and that advance motion backward or forward, those 2 motions are not independent. One depends on the other one, and so degrees of freedom have to be independent from each other. So actually, screw has 1 degree of freedom, cylindrical has 2. You have a spherical joint, you have planar joint, you have rigid joint, all of those I mentioned for you. You have a point moving on a curve joint, you have sliding on a curve, you have rolling on a curve, you have point to surface contact, universal joint, constant velocity or CV joint, you have gear joint, you have rack and pinion joint, and cable joint, okay? And so there are all sorts of these that you can create. So for example, let's say this revolute number 1, which is between the conrod and the input. Let's say I did not have this, okay? So here, I gotta delete that. And let me not delete those coincidences. So here I have created those, I have deleted that, and I want to recreate it but manually. So here I click on the revolute joint, and it says, okay, you need the 2 lines that are coincident and the 2 planes that are coincident. And these are exactly what we used for the assembly, right? So what we need is 2 lines here, one of them to be this line. So it's a good idea if you zoom in. So one of them is this line, which is on the conrod, and the other one should be on the input 1. So you see the 2 lines, they are on 2 different members. You can see on input and conrod. These 2 have to be coincident for concentricity, and then the 2 planes are basically this one and then this one. Now if you say okay, it should give you the same revolute joint, okay? And you see that's the same thing as the one I deleted. So you can manually create them as well, right? So let's say these joints that we have are good and the degree of freedom is 1, so everything is looking fine, and we go with the ones automatically created. Now it is time to look at the mechanism, do analysis on it, add input, and add commands or inputs. Here instead of input we call them commands, and then simulate the mechanism, generate plots, and so on and so forth. So the first thing you want to do is the mechanism analysis, okay? So if you go down here, it says mechanism analysis. So here we click on mechanism analysis, and it says degrees of freedom without command is 1, and degree of freedom with command is 1. Why? Because there is no command, there is no input. I have not provided any input here, so at the moment I cannot simulate it, but once I tell this joint how to move, then that is a command or input, and that determines everything. So degree of freedom of the whole thing goes to 0, right? So now how do we do that? Let's take a look. So now since we want to actuate this joint, we have to find which joint it is. So we go down here and see which one it is. Yes, and that is revolute joint 3. And clearly it is angle driven, so we check this, and we want this guy to be angle driven because it is a revolute joint. If it was prismatic, it would be length driven here, but you don't have the option right now. And then you limit it to go from one angle to another, right? So let's say from negative 360 to positive 360, right? You're allowing it to rotate, so you're giving it some range for the motion. And now it says, okay, now the mechanism can be simulated because you had 1 degree of freedom, and now you covered it by providing 1 input, or what we call one command. And now if you look, the degree of freedom is now 0, okay? And if you click on this again, it says now you have 1 command and the degree of freedom with command is 0. So the mechanism now, you see, can be simulated, okay? Now you can look at the mechanism, simulated, animated, and so on. How? So what you need is to click on this guy. It says simulation, okay? So you click on this, and it says, what do you want to animate? Say mechanism 1, and okay that. And then it brings for you this simulator window. So here, what you need to do is, I moved this slider from the center at 0. I moved it all the way back to negative 360. So when I go from left to right, it is motion in one direction, because if I go back and forth, then it is going to rotate in different directions, and that's most of the time not how this mechanism work. So, or you might just consider it is moving just backward, forward, but I prefer just going 2 full rotations in one direction. So I started at negative 360 and then go to positive 360. And now in order to create the frames for the animation, so you say animate viewpoint and then automatic insert, and then you click on insert, and here is the number of frames generated, and here is the basically amount of time allocated to each frame. So the smaller it is, it means the more frames it is going to collect during animation, and so you're going to have a smoother transition from one frame to the next. If you choose it like 1, you're going to have a jumpy video. It jumps from one position to the next, to the next, to the next. But the smaller you choose it, it is going to be smoother. Of course, it is going to be more frames, a little bit bigger video if you want to make it a video. But I go with some average number, 0.1. And now when you move this guy manually, look, you see the number of frames is going up from 1, and now it could create for me 84 frames. So now it has created 84 frames for me, and now if I OK that, now I have under the simulation tab something called simulation 1. Okay, so now I have this simulation 1, and the simulation 1 is something that I can play for you. So all I need is now click on the simulation player, and then if I want, I can change the parameters for the display, the sample time, and the temporization. So especially the sample time is important. Let me use 0.1, the same as we had before, and now click on run, and there we go. You see? So all of that animation I have generated, now you can see it with the video. So I generated an animation, and I could play it with this video player. Now there is another tool if you want to convert your simulation into a video, an AVI movie file that you can, let's say, insert in a PowerPoint or use for presentation. Because this simulation is clearly only for a visualization of the mechanism inside CATIA. If you want to see what it does as a movie, and you want to look at the behavior of this with like media player or something, and you don't have CATIA, or you want to share the result of your analysis with somebody else who does not have a CATIA, you have to convert them into something that people can open without CATIA. And so for that, if you remember, we were here that we created the simulation. If you expand it, there is this tool called compile simulation. If you click on it, it can generate a replay out of your simulation or an animation file. What are these? I'll tell you. For the default is generate a replay. What is replay? Replay is a type of basically animation, internal animation out of that simulation you did, which later you will use to generate the swept volume or the trace analysis. So for these two tools that we will talk about in a second, we need replay. But if you want to create animation files, you click on generate animation here. You can choose the type of basically compiler. I don't recommend you change that. Just go ahead and choose some location and some name for it, provide the step time, and then go ahead and let it generate the video for you. Okay, here the video is compiled, and although we did not choose a very small sample time, if you look at this video, you see that the volume is still large, 1.66 gigabytes. Okay, it's a very short video, but let me open it. Clearly, okay, it is going to take some big volumes, okay? So it's always a good idea if you ever want to share it with somebody to convert that AVI yourself with some online or some software that you might have bought into MP4. Otherwise, as I said, the volume is rather large, and you see it is quite slow because of the sample time. So maybe you need to bump up the sample time and use something bigger, and especially when you're compiling, to bring down the volume of this and make it act a little bit faster. So that's about creating an animation video out of it. Now, as I said, when you click here, it also allows you to generate a replay. And a replay is something similar to that video, but it's like an internal video that CATIA will use to do some analysis, like trace analysis or swept volume. Okay, so let me create one because we need it. So I'm gonna use a smaller sample time here to make it faster. And now you see under applications, there is now something called replay, right? And now I should be able to use that replay for trace analysis or for swept volume. So let's say if I click on swept volume here, it shows all the volume in the space that one member or several members are going to occupy, right? So if you don't want all of these members, then you click here, and maybe you just want to go with Conrad. I just want to see which area the Conrad is going to occupy. And then for reference element, if it allows you, you can select this. Now, if it doesn't, then it considers ground, so it doesn't matter. And here, if I say preview, this is all the volume that that member is going to occupy in the space as the mechanism goes through one full revolution. And this is very good for, let's say in robotics, you want to look at the workspace of the robot, right? Then you probably going to select all of the members and see all the areas that can be touched or occupied by robot points, or you might look at the areas that the end effector of the robot can hold, correct? Or let's say if you want to create a casing, right, an enclosure for your mechanism, you want to know how big that guy should be so that during the operation none of these members is going to have a collision with that enclosure. Then you might choose all of them and look at the volume swept by all of them. Okay, so the swept volume is a very good thing, and as you just saw it here, it works based on the replays. Okay, you need to have a replay to have this guy work. And now this trace analysis, it shows you the position of any specific point in the space as the mechanism moves. Again, this is very good for a robot. Let's say if you want to look at the all the points that the workspace, the end effector of the robot is capable of reaching. So this is very good for that. Or let's say you're doing a welding or anything else. It's a drawing mechanism or any assembly mechanism. This tracing is very powerful. So let's say here I'm interested in looking at the location of the centroid of this conrod. So I want to add a point in the middle of this conrod and then follow the location of that. So first let me hide the planes on this conrod. And now I'm going to go on this conrod. Right, this is that member. So I double click on this, and then I click on this surface, and then I click on a point, and I can put it anywhere I want. Let's just put it roughly in the center. So here I have added this point, and I go back here to DMU Kinematics, double click on the product, and now I can trace the location of this point. So I click on trace analysis, says what's the element to trace, and I say this guy, and the reference is the overall ground. The number of steps here are provided based on the number of steps in that replay. Again, you see you need a replay here, and then you say OK, and then in a separate window it shows the location of that point through all of those 85 sample points as the mechanism operates. Okay, and it should be 2 of these on the top of each other because the mechanism did 2 full revolutions. So here is the trace of that point during the operation of the mechanism. Okay, very useful. So here was these 2. As I said, they need a replay, and we created that using the compile tool. Now some of the other things we have is clash analysis, and you had the clash analysis also in assembly. So but you also have them here just in case you want to look at the clash. So you want to see whether your mechanism does have any clash or contact. Now, contact and clash are 2 different things, right? Contact means they can touch each other. Clash means they're going to hit each other. And clash is the one you want to definitely avoid. Contact, depending on the friction in your mechanism, you probably want to avoid that. Give it some small gap. Right now, we made all of these planes of these members touching each other coincident. So there will definitely be contact, but clash, hopefully, we don't have. And you can choose between 2 components, between all components, or anything for that matter. And let's just apply that. And if there is anything, it is going to show here. So you have 4 contacts, which is okay, but there is no clash, and that's the important thing. There is no clash, okay? That's the most important thing, so our mechanism is okay. And then, of course, there is also this distance and band analysis. So you want to see, for example, the minimum distance between 2 members, correct? And between 2 selections, let's say. And the selections are probably, let's say, this one and this one. And, well, you have to, let me do it again. So one of them is this, the other one you have to click in the window and select it and apply that. And it shows the minimum distance that these 2 members can come with respect to each other. Okay, the closest distance they will be 3996 mils. They'll never get closer than that. Okay, so this is also important if you want to make sure that these members are not getting super close to each other, if that is important to you, or whether they're going to have clash or something. So you have these 2 important tools. Now it's time to talk about the more advanced thing, and if you remember, it was about, now I want to provide a specific input for the motion of this input joint, a specific function of time, and based on that input, then I look at more advanced things like the position, velocity, acceleration of different members and everything, and generate plots. So this is the higher level task, but it is very important. And the first thing you need is a formula using which you describe the angle of this member, right? Remember, that's the only command or input that you have. Now you want to describe that angle via a function of time or a function of something else. Okay, so if you go here, right, under this simulation with commands that we did, there is also simulation with laws, and this is what we need. But again, before that, we need to create a formula. So we click here, and then if you look, one of the things you can control definitely is the angle, right? Mechanism 1 commands angle. This angle, if here is all of them, then make sure, because your input is an angle, this guy is the one you can control. So you choose that, and then you go to add a formula for it. And now let's say I want to make this guy to be some fixed RPM times time. So let's say I want to rotate the input with fixed RPM or fixed omega, and let's say that omega is 1 full revolution per second, right? So it's 360 degrees per 1 second. That's omega, and so theta, this angle, is going to be omega times t, correct? Plus initial angle. Now let's say the initial angle is 0. So the formula I want to create for this is simply theta, or that angle, if you call it theta, is omega times t, where omega is whatever you want. In this case, I decided 360 degrees per 1 second. So the way I insert this formula is like this. I say it is equal to 360 degrees divided by 1 second. That's your omega times t. Now for t, I need to find the parameter t here. So here it says parameters, and I go to times, and the only time parameter you have is this guy called kinematics time. So I double click on it, and now if you see, this is omega times t. If there is an initial angle, I can add it as a constant number. But let's say that's my formula, theta equal omega t, and I okay that. Right, and I okay that as well. So now I have a formula, and there is a law here under mechanism. If you see, there is this formula, and we can double click anytime and modify it to whatever we want. But first we created a law or a formula. We call it a law here. Now that I got the law, it is time to do a setup and then do simulation with law. So first thing we need to do is to tell this analyzer, which is this guy here, what kind of analysis we want, and give it some name, generate something. And so here we click on this tool, says speed and acceleration, right? So we click on this. And using this, we can tell it what is my reference part and what is the point I'm interested in, right? So what I need is go on that conrod and make that point. Let's say I'm interested in that point specifically. Because if you are after a linear position, velocity, and acceleration, you need a specific point. If you are after angular position, acceleration, or velocity, then you don't need the specific points, you need the whole rigid body. Okay, so in order to do a complete analysis, let's say I'm also interested in linear position, linear velocity, and linear acceleration of that point as well. So I select that point, I need that point. So here, let's click on this. It says, what is your point of interest? You say this point. What is your reference? Let's say this member. That's my fixed member, and you okay that. Okay. Now you have told CATIA what you want to do. Then you can go here and say simulation with laws. Okay. And now that you have a specific number of steps provided here, right? If you want, you can make it more to make it smoother. Let's say 40 steps is good enough. And if you click here on analysis, there is nothing right now. But if you say activate sensors, then here you can create basically what you want to plot, okay? So, and then you can add customize plot and look at everything. So right now, nothing is observed, which means you cannot generate plot from anything, okay? Nothing is really observed versus time from all different things you can measure. So first, if I click, You see, it ran it several times and it generated what it needs for plotting. And now if I go under analysis again, there is nothing here because I haven't activated any sensor for any measurements. So I say activate sensors, and now whatever I want to measure or plot, I have to make sure they are observed. Let's say here, I have revolute 2 angle, revolute 3 angle, cylindrical 4 angle, and so on and so forth. So there are some angles here. And if you want to see any of them versus time, you can see that. Then if you want to see here, this is the point that you selected, this guy. If you want to see the, for example, speed, acceleration, so these are the X, Y, and Z of that point. These are the location of that point. But if you go down also, you have the Vx, Vy, and Vz of that point. You see it says X linear speed, Y linear speed, Z linear speed. And this one that says linear speed is the total magnitude of velocity of that point. These are the components of it. And then you have the total acceleration and then the acceleration component. So this is A of that point. These are AX, AY, and AZ of that point. So you see position, velocity, and acceleration. All of these guys are for that point. And you can look at any of them that you want. Let's say I'm interested in the magnitude of the velocity of that point. So you see I click on it, the observe from no goes to yes. I'm interested in total acceleration of that point. I look at it. I'm also interested in this case, the Y and Z of that point. So I say I want to see the Y of it, I want to see the Z of it, the X of it does not change. And I'm also interested in looking at the angle of revolute 2. Now, if you don't know what revolute 2 is, you have to go here under joints and see what revolute 2 is, what is revolute 3. So 2 is between output and conrod. What I need is between ground and input, which is revolute 3 angle, that's good. And then between output and ground, maybe cylindrical 4 angle. So this one and this one, these are good. Now if you want it between the revolute 2, you can also look at that. So whatever you want, activate them, right? And now let me go back here, run it. So now I have generated data because the sensors are active, and when I run the simulation here, the sensors are active to generate data for me, right? Okay, so they are observed, and now if I want, I can click here on graphics, and all of those guys that I have selected, I can see them all versus time, and with different legends, of course, right? Different colors mean different things. Now here I'm looking at too many things at the same time, and this graph is just too busy. So maybe I just look at one of them, and let's say that is, for example, the linear speed of that point, or linear maybe acceleration of that point, versus time, correct? So let me make everything else no for the moment being. Let me just maybe it's between input and ground revolute 3. That is good, but not too many other things. So there was one here, 1 and 2. Good. Run it one more time, and then look at that result again. Okay, so you have to activate sensors. Look at the graphics. Now clearly you can see the yellow, which is the angle of the input link, clearly does change linearly versus time, theta equal omega times t, and that is very obvious. But if you look at the total acceleration of the center of the conrod, you see how it is variable. It is changing versus time. Or if you want, for example, you could have looked at the angle between the output and the ground, which is cylindrical 4. So you can look at this one if you want and do that one. Let me go back. And by the way, whenever you get a bunch of data, you see I'm going back and forth, then that's why you have a bunch of data in two different directions. Before you run it forward and get new data, what I would do is I would clean up my previous collected values. Okay, so you go here to history, right, and you say clear. So any previously generated data will go away. And now when you run it, those sensors will be populated with new data. And now when you click on graphics, your results are way more visible and nicer, meaningful. And you clearly can see, although the input angle versus time is changing linearly as it should, the output angle versus time is definitely not constant, not changing linearly. And even if you look at the acceleration of that, angular acceleration of that, nothing is constant for the output. Okay, and this jaggedness you see is because of the time sample we chose. The smaller time sample you choose, the nicer plots you will get. Okay, these are quite jagged because you don't have too many data points. So if you want, go ahead and bump up the number of steps, go to history again, clean that up, run one more time, and look at the thing, right? So here we go. Now it is going fast, but the number of steps are more. So you see now your plots are getting a little bit nicer. So this is plotting anything you want versus time. Okay, and if you have more than one thing observed, then they're all on the same plot using legends. Okay, but sometimes maybe you want to plot one entity versus another one, and you don't want to plot all of these guys versus time, right? Because right now I'm plotting everything versus time. What if I want to, let's say, plot, for example, y of this point versus z of that point, right? Correct? Can I do that? Sure. So what you need is here, or I want, let's say, the speed of one of these points, speed of the point, or maybe, I don't know, the output angle versus input angle. So I want to plot stuff versus, let's say, input angle. Then what? So what you need is here, I want to look at y and z of this guy. I first move the mechanism back, go to history, clean everything up. Now I can only see those two, and that is amazing, right? And I can plot now. If I click on run and look at graphics, it's gonna be each one of those two positions versus time. But I can go under options, and here it says, do you want everything versus time, or do you want customize? And I say I want to customize, add one for me. And it says, okay, what is your x and y axis? Okay, so here right now they're both the angle of the input, but let's say I want what? I want y to be the x-axis, and I want z of the point to be the y-axis. So I want to plot z of the point versus y of the point. And this is one of my customized plots. I call it curved 1. Right, now when I simulate my mechanism, if I click on graphics, you see now it is z of the point versus y of the point, and this is the same as the trace of that point almost, right? It should be exactly, but it depends on the number of data points that you have for generating the curve. So you can create customized plots. Okay, and as I said, you can go ahead and change the input formula for that angle to anything else that you want, or you can actuate any other joint all you needed in the beginning when you went and clicked on, I guess it was this one, and you said this is angle driven, so you put your input on that one. If you want, you can turn that off, right? And now here, because we have so many simulations and everything, it does not allow me easily change it, so I have to go and change and delete this simulation and stuff. But in the beginning, as I said, if instead of that Revolute 3 you activated, let's say you made this one to be the input, right, which is between ground and output, you can make this one angle driven. Now you see here it says this one is also length driven because it's a cylindrical, so it means you can move this, but definitely you don't want to do that. You want to make sure this is angle driven. Okay, so by choosing the appropriate input, output, making sure the degree of mechanism, the degree of freedom is 0 after providing input, and it tells you that the mechanism can now be simulated, then you can do manual simulation, create videos, do the tracing, swept volume, create a law, do the speed, acceleration, position, or anything else, plots of them versus each other or versus time, customized plots. So as I said, you can also convert your assembly into joints automatically, or you can create joints manually. And these are most of the important tools that you have in DMU Kinematics. One final thing you might be curious about is what is this one, and this is just to turn on or off the clash detection, right? So if there is any clash, right now it's off, so the mechanism will be simulated regardless of whether there is a clash or not. But if you go ahead and make it on, then it is not going to simulate the mechanism if it can find any clash during the simulation. Okay, so you can turn that on or off, and based on that, you should be able to look at the simulation results. Okay, so we'll stop the lecture here, and I will see you in the next video. Thank you.